Okay, so let's continue. Second example, 6-point differencing. But before that, in example 1, we have seen this 6-point averaging. So this 6-point averaging system, it's used for what? Smoothing out, which attenuates high frequency and amplify low. So to check this, we apply 3 inputs to check 3 type of inputs. So let's say, for example, input B, x of n is a cosine wave, but it is low frequency. This is a low frequency. C, part C is, as you can see here, it is high frequency cosine. So when you apply through this system, I will show you how to, using MATLAB, how we can determine the response of this system. So you see on the result, this low frequency signal amplitude 1, but part C, high frequency signal, amplitude is only what? 0.2. So what we understand? This system amplifies low frequency signals but attenuates high frequency signals. What this system, we call it what? 6-point averaging field system. Okay, second example. 6-point differencing. This system is called what? 6-point differencing. So six-point differencing system. So it takes input signal. When I say input, x of n, and after processing, it gives us output sequence, new sequence, y of n, from the difference equation. The difference equation is given here. It is what? X of n, the present input, minus the x of n minus 1, input before 1 time unit. First, we take this difference. Then plus x of n minus 2 minus x n minus 3. These two samples subtract each other. Okay. Then plus, look here, these two subtracted. Then we have plus here. The last, this x of n minus 2 and subtracted x of minus 3. Then plus x of n minus 4 minus x of n minus 5. Okay. So all these 3 signals added together and divided by 6, it becomes average, right? We need average. So divided by 6. This system with this difference equation is called 6-point differencing system. Okay, 6-point differencing system. How to construct this? So x of n here, x of n input delayed by 1 delay element, we get what? We get x of n minus 1. Here x of n minus 1 multiplied by minus 1. Okay, look here, x of n minus x of n minus 1. Then it will be added together with the x of n. x of n is positive. X of n is multiplied by what? Positive 1. Here you see, and the coefficient of x of n is 1. Coefficient of x of n minus 1 is negative, so I multiplied by negative. Next, I need the previous sample, so again delay the input by another delay element. We get what? We get x of n minus 2. Is it positive or negative? X minus 2 is positive, so it's multiplied by positive 1. Okay, plus comes here, comes here. Now, how about again delay by 1 to get what? To get x of n minus 3. How about x of n minus 3? As you can see here, the coefficient is negative, so I have to multiply it by negative 1. Then add together the signals. Then delay this by 1 again. When you delay it by 1, we get x of n minus 4. Sample before 4 sample period. X of n minus 4, as you can see here, it is positive coefficient. So it will be positive 1. Then delayed by 1 again. We get finally what? The last sum, x of n minus 5. What is the coefficient of n minus 5? It is negative. So multiplied by negative 1, added together. All these signals added together, and the whole here, as you can see here, divided by 6. So I need one multiplier here with a multiplication constant 1 over 6. It will give me what? Y of n. Okay. So output is 1 over 6 times the summation of x of n minus, you see here, x of coefficient of x of minus 1 negative, so that's why I put negative. So x of n minus 1 multiplied by negative x of n minus 2 positive constant coefficient, so it's positive, added together, and so on. This design will come in chapter 4. So this system, is it recursive or non-recursive? Again, it is non-recursive. Why it's non-recursive? Because again the output depends only on input at this time and past inputs. The previous outputs does not affect the output, because the output does not depend on past value of outputs. I'm not talking about inputs. So this system, to the opposite to the last one, it attenuates low frequencies. It attenuates low frequencies. And it amplifies high frequencies. Amplify high frequency signal components. Okay. The first one, the 6-point averaging, it attenuates high frequencies, right? But this one, it amplifies high frequencies, but low frequencies are attenuated. So when you see this example, the previously, as you can see here, the low frequency is amplified, amplitude, high frequency part C attenuated, only amplitude 0.2, right? Now when you see the second system, which is called point differencing, if you apply the same inputs, this input is low frequency. What is the amplitude? Only 0.2. High frequency, now amplitude 1. High frequency in this case amplified, low frequencies are attenuated. Okay, so how to determine this using MATLAB? I will show you how to write your program. So this is the system. What we have to do? This is our system. We apply the first input here, cosine. What will be the output? So this is low frequency. Then we apply another cosine, which is high frequency. We check the outputs. Okay. What is the system? The system is represented by this difference equation. So you can see how difference equation is important. It is used for the design purpose. You see here, we are designing this system using components, adder, multiplier, memory elements, and so on. So whatever input you apply here, it generates output, right? It's non-recursive and it attenuates low frequencies, but it amplifies high frequencies. But the first one, low frequencies are amplified, but high frequencies are attenuated. Okay. Now let's see some more examples. In this case, we'll see recursive. Previously, we have seen systems which are not non-recursive. Now, let's see systems which are recursive. So this is low pass filter, digital filter, but it is recursive. Okay. In this case, it amplifies what? Low frequencies. It attenuates, rejects high frequencies. So this is nothing but a low pass filter, moving average filter, low pass. Low pass means low frequencies are amplified, high frequencies rejected. But this design is non-recursive design, non-recursive, which means output does not depend on past value of outputs. When the same system, low pass filter, but this one is recursive, which means this is our input. What is the difference equation? Y of n is equal to 0.95 yn minus 1 plus 0.05 x of n. Okay, look this difference equation. So output at present time depends on what? Depends on this factor. What is this? This is past value of output. Past previous value past outputs. How about this part? It's input. Only the present. In this case, only the present x of n. There is no xn minus 1. So you see here, this system is called recursive. Why? Because it's recursive. Because output depends not only the input part. There is previous outputs also affect the present output. So the system is recursive. It is what a recursive system. And similarly, it amplify low frequency, and it attenuates high frequency. Attenuate high frequency. So now if you want to construct this system, this is the input So this is our output. Output delayed by 1, the output part, y of n, right? This is output part. We will see this in chapter 4. This is input part. So here I delay the output part, this part, by 1. So we get what here? Y n minus 1. Alright, it's delayed by 1. Then multiply this by how much? From the difference equation, you see the coefficient 0.95. This one, go back and added with input. Input first multiplied by how much? 0.05. Look here. So output is equal to y of n is equal to, this is a feedback now. We have feedback. It's first delayed by 1 because in the equation you see yn minus 1. Then multiplied by this, go back here, input x of n multiplied by 0.05 x of n. So it will give us the output. So this is our system. So inside this system, how many memory units we use? Only one. Only one memory unit here you see. How many multiplier? Only one multiplier. How many other? Only one other. But the previous non-recursive low-pass filter, you can see here, it's also a low-pass filter. But how many others? 1, 2, 3, 4, 5 other. To construct this, we need 5 memory elements, unit delay elements, unit delay. We need multipliers 1, 2, 3, 4, 5, 6, 7 multipliers. So you see, we are using so many components to construct this system. But in the recursive case, with one multiplier, one adder, one shift unit delay element, low pass filter can be constructed. So recursive design is more economical. When you design any digital system, as much as possible, we need to minimize number of components, right? Same system you can design with 100 components, with 5 components. The system doing the same job, but good designers design using minimum components. Minimum components means low cost. That's why these days you see electronic devices, the price is going down. If you see smartphone, previously it was very expensive, now it's very cheap, right? TVs, computers, price is going down because the design is improved. With minimum number of components, we can design systems. So it's also low pass filter. You can check here. How do you know this low pass filter? Let's apply again x of n cosine with low frequency. How much amplitude? 0.2. If you give it high frequency, C, you see the amplitude? 0.05. It attenuates even high. This is very powerful filter. The first one, this moving average, when you see the signal is attenuated up, high frequency attenuated up to what? 0.2. But the recursive one attenuate into much farther. The amplitude, this high frequency, attenuated to very low value. Okay, so let's see one more system. In this case, it is recursive again. Okay, this is the opposite of high pass. In this case, it is, sorry, in this case, it is high pass filter. Okay. Previously, we have seen low pass filter, right? What is the equation for low pass filter? y of n, this is for high pass filter, is equal to, this case it is negative. The coefficient is 0.95. Y of n minus 1 plus 0.05 the input. This is difference equation, right? Difference equation, as you know, equation for representing discrete time systems. This is input x of n. So this system is also recursive. Why? Because the output depends on the present output depends on past value of outputs. Very powerful design. This feedback recursive design. It's high pass, so this is also recursive. It's high pass means it amplify high frequencies. Okay. High frequencies are amplified and low frequencies are attenuated. Okay. Attenuate low frequencies. Okay, so what's the equation difference you see between high pass and low pass? Only this negative sign. In the case of low pass, this is positive. You see here, 0.95 is positive. So this coefficient is positive. In high pass, this coefficient is negative. Just making this coefficient negative changes low pass into high pass. So in your design, what we should do? Mostly this you can implement using software. If you make this negative here on this diagram, 0.95, it becomes high pass filter. High pass filter means low frequencies are attenuated. Let's check. You see now the low frequency part is attenuated. High frequency part is amplified. Okay. This is a recursive high pass filter. What we call it a recursive high pass filter.